Everybody, it's 314 React here, and today we are looking at my latest tech project, which is Fragment, a benchmarking tool inspired by 3D Mark. So a benchmark essentially is a way to just measure the performance of your system and compare it to other systems. Also, if you overclock it or upgrade parts of it, you can run the benchmark again to see how much it's improved the performance. Now, a number of months ago, I made a series of videos on 3D Mark, going from 3D Mark 2000 all the way to the very latest version. And while doing these videos, it inspired me to try and make my own benchmarking software using Python and OpenGL. So I sat down with ChatGPT and began to work on some code in March 2024, and here we are nearly a year later, and finally we are at a initial release. So as you can see, it's got a GUI layout very similar to 3D Mark. I used that as a sort of inspiration, different tabs, settings, scenarios, results, as well as the commonly used options on the side here. This will work on PCs with Windows 11 and OpenGL 3.3 and beyond compatible GPUs, but I also want it to work on Raspberry Pi, so it will work on Raspberry Pi 4 and above with the operating system Bookworm. That's what I've tested it on, and it works there. So it's a nice cross-platform testing system. It's not to be taken too seriously. The numbers produced from it won't give a really accurate idea of your system's performance like an actual benchmarking piece of software will, but it's just a bit of fun, and I wanted to learn a bit more about how graphics work on a shader level, like at the actual code level of making GLSL shaders. We've got the main buttons here. We've got a nice little icon there, nice little icon in the corner. All the main buttons always available on the site here, so you can always run the benchmark for wherever you are, you can run the demo wherever you are, and you can look at the about page wherever you are. The about page again has the icon there, the name, the versioning system, which is automatically updated via a GitHub workflow when the main branch is merged to. It's got links to my GitHub, Hackstone, Electromaker. It's got a caution here about how resource intensive Fragment is. I imagine it's not the best optimized thing and can probably cause some heat buildup on your hardware, so please do use it at your own risk. There's probably also quite a few bugs in it and possibly memory leaks, so also be careful about that. Use it at your own risk and proceed with caution if you want to use it. Appearance mode here, you can flick between light and dark mode. The light mode, like the icon, is the coloring of my YouTube channel icon, so I've tried to keep that on brand. And there's also UI scaling here, so you can change all the size of the fonts and stuff like that, which is really handy for different resolutions. It should also pick up your operating system's appearance mode and switch to light and dark according to what that's set to. So if we look at the main settings here, you've got the resolution, which goes all the way from 640 by 480 all the way at full screen. You've got MSAA levels all the way from 0 to 8, and isotropy levels all the way from 1 to 16. Shading model, where you can select diffuse, Phong, or physically based rendering. You've got shadow quality ranging from none to 1024 by 1024, 2048 by 2048, and 4096 by 4096. Now this is the resolution of the shadow map. Obviously the higher the resolution, the better the shadows will look, but the more memory and GPU it will take up. We've also got a particle render mode here, where you can flick between CPU, transform feedback, and compute shader modes. I've also tested this as much as I can with a reasonably new AMD GPU, and it seems to work fine. There just seems to be missing MSAA and anisotropy. The compute shader will work with NVIDIA and AMD GPUs that support OpenGL 4.3 and above. The compute shader will work on my AMD built-in GPU, but the CPU and transform feedback shader should work on most GPUs and are the only two that will work on Raspberry Pi. Obviously the Raspberry Pi doesn't have any compute shaders as far as I'm aware, and only supports up to OpenGL 3.3. Obviously you can enable VSync here, which is off by default. You can enable sound, which is available only in the demo shimmer. So let's have a look at the scenarios. So you've got Ethereal here, which is an environment map bump mapping test. Eidolon, which is a transparency shader test, which uses the same EMBM shader but has a camera behind the model that moves with the main camera and renders to a texture, which is then put over the top of the model with refraction and distortion to make it look like the model is transparent. Treadlock, which is a parallax shading test inspired by Gran Turismo, where there's a spinning tire and all of the parts of the tread are enhanced with parallax mapping to make it look like there's extra geometry when there actually isn't. There's Gelidus, which is a reflection test. It's a really nice water shader which uses environment mapping and dynamic normals to generate a reflection. And then there's Baryon, which is the particle system test. So I've tried to make these tests as abstract and as interesting as possible, while still also being plausible that they could be part of a video game. So let's run some Ethereal. What you can do is select your benchmarks here, and then you can go to your settings here, and you can change the settings and run the benchmark without having to keep flicking back and forth between tabs. That's why these buttons are over here, so it's really handy. What we're going to do is crank it up to 8 times MSAA, make sure we've got all the shadowing up to the absolute max, and put the compute shader on. So when we do hit the particle rendering, we can see the very best performance and amount of particles. So let's fire up some Ethereal. And so here we are. You can see the shadowing there on the side with lights there as well. That's because the shadow mapping is only done by the first light in the system, so this light here is causing the shadow, the rest of them don't count towards shadow mapping. And I've tried to make a really nice sort of crystal texture here with the PBR, make it nice and shiny and make it look like it's mystical, magical sort of environment, kind of inspired by things like Age of Wonders. Now, all the textures and skyboxes and stuff for this have all been generated, even the objects have been generated by ChatGPT, because I don't have the artistic skill myself to make them, so ChatGPT really helps with that sort of thing. And I've also used other tools to help out, to make the music, to make the normal maps, the displacement maps and roughness maps, stuff like that. And there are details of that in the GitHub and the Hackster and Electromaker pages, which I'll link in the description. And you can see once the test has run, it spits out the benchmark results here. So it gives you the average FPS at the top, and then it gives you a really nice Matplotlib chart, which has really nice smooth lines in it showing the FPS over time. It shows the CPU and GPU usage over time and gives you an overall performance score. As you can see here, that performance score is calculated by the overall average FPS, which is all of the FPS gathered up divided by the number of benchmarks, and then times by 10 for a scaling factor, and then it returns that as the performance score. This score isn't meant to be taken too seriously as a comparison. It's just kind of a fun little number that can be given out. You can sort of use it for comparison of performance, and when you dial the settings up and down, it will adjust that score, but it's not to be taken too seriously. As you can see there, it relates fairly heavily towards the FPS there. Not sure how 3D Mark does their scores, but I'm sure they do a much better way. And there's also no differentiation at the moment between CPU score and GPU score. You can sort of see the usage here. You can also see it's got the specs of the machine at the bottom here, and the CPU, GPU, and RAM. Now you can see the GPU usage here. If you're running an AMD machine, you won't see any GPU usage, or you'll see the GPU usage of an NVIDIA discrete card, but it'll be much lower because it can't measure the GPU usage of an AMD card at the moment, or the ARM GPU on Raspberry Pi, which is unfortunate because I've tried to look for libraries that will measure those and also bring the data up here, but at the moment I can't. So if you're running this on AMD, you pretty much just have the CPU score. If you're running it on Raspberry Pi, you'll just have the CPU score, but you'll still get your overall performance score because that's grabbed from the FPS over time. So that was Ethereal. Let's go to Eidolon. Now this one was inspired by the stealth shader effect from Halo. So you can see how the camera behind it is rendering to a texture and then wrapping that texture around and then doing this really nice distortion and refraction, which is based off of the bump map of the texture. So it looks like it's see-through and refracting, which is a really nice effect. And none of these benchmarks are going to be too heavy duty in terms of how good they look or anything like that, because as I say, they are meant to be portable to Raspberry Pi. And there you go, you can see the sort of lake behind it there. There's a bit of oddness with how the texture wraps here because of the UV mapping on this sphere. But I did it as best as I could. And there's also some issues with the skybox there because of the way the skybox is generated. You can see more details about that in the links in the description. So that was Eidolon. There's also Treadlock. And just while we're here, you can see all these previews, obviously, of the benchmarks with a nice little shadow behind the preview there. And you can even hover over the demo and get a preview of that as well. So Treadlock is inspired by Gran Turismo 7. When you preview the tyres in Gran Turismo 7, you can see them spinning around with really nice rubber textures on them and all the details in the tread. So here I want to recreate that. There's a slight issue here with the seam on the model. Tried my best to get around that, but found a way to get around that in Blender yet. But that's not too bad. But as you can see here, the Parallax shader is really nicely handling those treads, making it look like they are proper 3D. But of course, they're not. It's pretty much just a torus shape with a hollowed out middle. But the Parallax shader works really nice to make it look like these treads are protruding. There's also a really nice shadow there in the middle from that shadow mapping. And a nice rubber effect from the physically based rendering. This is one of my favorite scenarios that I've made so far. Again, as you run the different benchmarks, you can see the different effect it has on the GPU and CPU. And then there's Gelidus, which is just a really nice water shader. Reminds me of the sort of water you'd get in Halo 1. Again, another influence there. And also, while we're here, you can see along the top in the window, there's printing out the live FPS, live CPU usage, and the live GPU usage. So while you're running the benchmark, you can see that. In future, I may add in system temperature and stuff like that. Yeah, this is a fairly basic test, but it looks really nice. And this uses a surface renderer instead of a model renderer. Again, you can see all the code in the links in the description. Again, some of these skyboxes could do with a little bit of improvement. Now we go down to Baryon, which is the particle system test. So this is really cool. So at the moment it's using the compute shader, so we're getting a really high FPS. And you can see there the physics of the particles are calculated, so they're bouncing off of the sort of windscreen of the spaceship that's flying through right now. And you can see them changing color from red to green and then fading away. Now the particle renderer is all configurable, so you can change the physics, how and where the particles spawn and how they behave. So you can create all manner of sort of particle effects. And you can see there the CPU usage is relatively low and the GPU usage is relatively high because it's all being done in the compute shader. So yeah, I'm really, really happy with that one. And we'll see the difference with the CPU and the compute shader versions when we run Shimmer. Because yeah, you can flick it to the CPU, run it on that. And the CPU will look pretty much the same for Baryon. It will just run slower. But for Shimmer, this is where we'll really see the difference. So we'll switch sound on for Shimmer so that we can hear the sort of ambient music that I made for this using an excellent piece of software called Audio LDM2, which is available on GitHub. And all the tools that I use for this are in the README and on the Hackster page. And it's basically a prompt to music piece of software that I use to make a nice ambient sound to go alongside the demo here. Fire this up. Now this is a demo, so it doesn't have any output in terms of performance or metrics, but it does have the live FPS, CPU and GPU. And as you see, there's so many rain particles flying down here from the compute shader. There's a EMBM bump mapped pyramid here on the right with a camera that's facing backwards and then rendering that over to create a reflection. And it's also semi-transparent, so it has a metallic surface with a reflection in it. And then there's this pyramid here with a camera facing the other way and transparency effects, so it looks like it's see-through. And then there's this pyramid here which has the crystals on it, but they are running with a parallax shader, so you can kind of see the depth of the crystals there. There's some errors with the parallax shader, but I think that's to do with the UV mapping of the pyramid. I need to try and improve that at some point. And also you can see here the shadows from the shadow mapping on the ground, self-shadowing as well as shadowing onto other objects. And you can also see the depth of the waves there because the water renderer here is using parallax occlusion mapping, where the depth map is being dynamically generated in the shader to cause the waves, and then the parallax shader is being added to that to displace the textures to make it look like there's actual physical waves, and that shows off as much of the features as possible. And I may add to that demo in future. And then what you can do is flick it to transform feedback mode and run it again. And this time we have the sound turned off. But as you can see here, kind of see the wobble of the shadows along the surface normals. And you can see how fewer particles there are when in transform feedback mode, because transform feedback mode just can't handle as many particles as the compute shader. The CPU mode can handle a couple of thousand, the transform feedback mode can handle tens of thousands, and the compute shader can handle millions of particles. But I think I need to optimize this a bit more because it does run really slowly even in compute shader mode. You can kind of see some of the particles flying down here, but not a great deal of them. Again, you can see a lot more of those waves there, how they're distorting, so they look like 3D waves. And the shader for the water has configurable options like wave height, how many waves there are, stuff like that. So it's all completely configurable so you can get different effects on the water surface. I just love that refraction there, that's so cool. Then if we flick to CPU mode, you can see there's just barely any particles. You may see one or two fly by. And ironically, this one's running smoother than transform feedback, I think, just by the fact it's just rendering less particles on the GPU. But if we were to crank up the amount of particles, it would start to strain the CPU. Although CPU usage isn't too bad at the moment. So maybe in a future update I can actually crank those particles up on the CPU side. But it's still pretty heavy on the GPU there. Yeah, there are particles being generated, rain particles being generated on the CPU side, but just not that many. So that's something I may be able to look into in future, is to actually increase the amount of particles on the CPU side. But for a direct comparison, if we load up Baryon again with CPU mode, see here it's in quite a lot of CPU, very little GPU, and it's running at about 20 frames a second, and the particles are moving quite slowly, so that's about 20 frames a second. And if we crank that up to transform feedback, you can see it's running at 434 frames a second there. So that gives you a general idea of how much better it runs when using transform feedback. And then again, if we crank it up to compute shader, you see it's running at 560 or so FPS. And obviously, as you change these settings, it changes the amount of pressure on the GPU, which will change the performance of shimmer. So if you were to turn down the MSAA level and then the shadows a bit and run transform feedback, you do see an improved FPS because there's obviously less pressure on the GPU, the anti-aliasing and stuff like that. So it has a lot more free cycles for handling the transform feedback particles. And that's what this is designed for, just to play around with these settings and see how the different settings affect the performance. And then of course running the benchmarks, getting your results out and seeing the differences in CPU and GPU usage, the FPS, comparing your performance score between runs. The other cool thing is you can flick between diffuse, Phong and PBR, so physically based rendering. So if we knock it down to Phong, we can see how shimmer looks with that. As you can see, it looks a lot more basic because we're no longer taking the material settings from the MTL files and using that to determine roughness and metallic. And we're just doing a much more basic sort of sampling of the diffuse textures and applying Phong shading to them. So you've got the nice shine from the Phong there. So it looks a lot more basic, but you still have the shadowing present and the refraction present. And it does show a lot more of the flaws of the parallax mapping here. The parallax mapping is really clean on the tire, but not so much on the pyramid. Again, I think that's just due to UV mapping and the crystal texture and the displacement map of the crystals. But it still gives a good effect at certain points where it does actually look like the crystals are proper 3D like there. And of course finally there's the most basic form of rendering, which is diffuse shading, which is even more basic. Still has these nice effects, still has the lighting and shadowing, but there's no Phong specular shading. It's just a very sort of basic sampling of the diffuse textures and the environment map. So it doesn't look as advanced. But interestingly, the frame rate is very similar. So I think there may be another bottleneck with this demo. And I think it's because of all the different renderers and the way I load them in Python. It could be something I need to optimize on that side. But yeah, that's a quick run through of Fragment. You can check out the links in the description. This is the GitHub here. It's got a nice README going through all the details of how this works, what it looks like, purpose of it, the architecture of it, prerequisites, setup, configuration on a Raspberry Pi, running the benchmark. There's obviously the caution here about how it can be quite heavy on systems and it may cause excessive heat buildup. So yeah, again, use this at your own risk. It's got the disclaimer about the performance score. It's how to test it because there's a test suite built in as well. It's also got information about known issues as well as how to make your own benchmark scripts. You can actually add your own benchmark scripts to this. I've tried to make it as modular as possible. So you can see here, you can construct it in this manner of taking this template here and then adding renderers in. And the way it's been configured is there's a superclass called renderer config, which has all the config under it, so you can't incorrectly put in wrong config, and all that config for the different renderers is stored under here. So you can kind of try and build your own benchmark with it, and this will start you off. And you can see here, you can just add them in, add the renderer, do the translation of the renderer, rotate, scale the renderers, stuff like that. And what you can do if you want is do a pull request, add your own changes in, and there's a GitHub Actions workflow that lints and tests it on the pull request side. And then if it gets approved, it will go over and be tagged and bumped on merge, where I have a script that determines how many changes have been made and bumps the version depending on whether it's a patch, minor, or a major amount of changes. You can see here, if it's under 250 lines code change, then it's a patch. If it's 250 to 2000 lines, it's a minor patch. And if it's over 2000 lines, it's a major patch, and we'll bump the version as necessary. There's all the acknowledgements here of all the tools that I used to build this. ChatGPT, the material map generator, audio LDM2, sphere to cube, and real ESR GAN. There's also links to the Hackster and Electromaker pages, which have the full write-up and extra details about how I made this on it. So yeah, if you feel like running this, feel free to check it out and follow the instructions on installing it. Again, use it at your own risk. There's not an installer or anything like that, so you will need to install Python and install the packages and set all that up. So if you're pretty knowledgeable about Python and coding, then check it out. Can't guarantee that it'll work, and there's probably bugs and memory leaks and stuff. I have seen definitely on Raspberry Pi where there was a memory leak and it just completely crashed out, so do be careful with that when you're rerunning especially the demo. Now what I'm going to do now is do a full run through of everything and just show how all the results are compiled at the end. And so here we are with the full results of all of the tests out. You can see here all of the benchmark results are up here in this nice little text window, and all of the Matplotlib charts with the nice smooth lines have been printed out. Now these actually get rendered to TK images and then slotted in one at a time, so they're not the raw Matplotlibs. This helps the scroll smoother, because I found when you're doing raw plots in here, scrolling up now will be incredibly slow. But yeah, it gives you the full view here of the FPS over time and the GPU, CPU usage over time. Orders them all really nicely. You can see all of the results, and here you can see the overall performance score, which again isn't meant to be taken too seriously, as it's very closely related to the overall average FPS. So I may change that in future to make that a bit more of a meaningful score. And that's Fragment. I'm really quite proud of what I've done here. There's still a few more things I want to add to it. There's a Bay 12 benchmark that I want to make a alien-styled first-person shooter benchmark out of. I'll be doing that in future. It's going to take quite a bit of development to do. So I just wanted to get a kind of version 1 release out for now, and then try and fix bugs and add stuff to it later. Really happy with how it turned out. Like I said, it's been about a year's worth of work. It's not just a simple download and install. So if you are a bit more comfortable with that sort of thing, it's worth checking out and seeing how it runs on your system. Again, run at your own risk. There could be memory leaks. There could be issues with overheating, especially on Raspberry Pi. So please do be careful. That's pretty much it for now. Just wanted to do a video walkthrough of this to go alongside my write-up. Please leave a like, leave a comment, let me know what you think. Subscribe, hit the little bell, really helps the channel. And stay tuned for new videos on tech and video games. New video every week. Hope everyone's staying safe, and I will see you in the next video.